E aku nui e aku rahi tēnei te mihi mai haki a koutou. Kei te mia hoki hokainga o tēnei rohe, ara ko ngai tua huriri, nā rātu tiaki aho. Kei te mia hoki a tangata whenua, kei te mihi aho ki a korua e ngā rangatira, Emmeline, Pat Dahlstrom, korua ko Eric Dahlstrom, ki a koutou, no mai, haere mai, ngā mihi nui ki a koutou. Greetings, good evening, and welcome to you all to the Space for Planet Earth Challenge, leveraging space technologies to address climate change. Ko Kaila Colbin tokuingoa. My name is Kaila Colbin. It is my absolute privilege to be your MC for this evening. I want to acknowledge a few folks, the folks I acknowledged in my mihi just before. I want to acknowledge Mana Whenua for the spot that I am broadcasting to you from, the people who hold tribal sovereignty over this land. That is Ngai Tuahuriri. I want to acknowledge Tangata Whenua for all of the teams and everyone involved with the challenge, the Indigenous peoples who represent all of the areas that are covered through this evening's activities. I want to acknowledge the powerhouses behind this evening's not only this evening's event, but the entire Space for Planet Earth Challenge. That is the wonderful Emmeline, Pat Dahlstrom, and Eric Dahlstrom. You two are amazing. We all know this would not have happened without you. Thank you so much for all of your hard work. And finally, I want to acknowledge the judges who are putting their discernment on the line for us this evening. Angela Kennedy from the U.S. Embassy, Boyd Warren from ChristchurchNZ, Raphael Cargren from Pacific GIS and Remote Sensing Council, Nick Brewer from Callahan Innovation, Tanya Harrison from Planet Labs, John Taylor from Consegna, and Emma Comrie Thompson from Rocket Lab. Thank you so much for being part of this event. I will tell you, I am not a climate scientist, but I have been following the science for some time. In 2009, I had the honor of training with former Vice President Al Gore to deliver the Inconvenient Truth presentation. I trained as a climate project ambassador. In 2017, I ran TEDx Scott Base in Antarctica, focused on climate scientists, and through that event got to engage with a number of the folks working on the front lines of climate scientists, climate science, glaciology, et cetera. And what has been abundantly clear certainly since I got involved, but to many people for decades prior, is that we are absolutely in a climate emergency and we need all hands on deck if we want to have a hope of being effective in our response. The good news is that today we've got unprecedented access to satellite remote sensing data and technology that can help us better detect, monitor, and measure the changes that are happening in our world and on our planet. We also have the computational capability to analyze this data so we can make better management decisions and create policies that can help us reverse some of the damage that we've caused to the planet. Now, satellite remote sensing has been the principal method of monitoring the impact of climate change, but now we can use that satellite data as well as wider access to computing and analysis tools to enable researchers to develop new solutions. This prize challenge is used to reward successful advances in state-of-the-art while creating opportunities for space education and outreach, as well as stimulating economic growth and development in the sector. So here's how it's going to go this evening. First, we're going to welcome some of the wonderful champions and supporters of the Space for Planet Earth Challenge. Then we're going to hear the pitches from our finalists, no pressure teams. Then we've got two categories this evening. We've got a high school category and a university category. Each of those groups was given a different problem statement. I'll share those problem statements as we head into those categories. After those pitches, we'll take a 15-minute break for the judges to deliberate, and then we will come back for the awards ceremony. So with that, it is my great pleasure to introduce someone who is a huge champion of innovation and someone who I know feels acutely the challenge that climate change represents to our city, Otautahi Christchurch, to our nation, Aotearoa, New Zealand, and to the world. Please welcome Her Worship, the Mayor of Christchurch, the Honorable Leanne Dalzell. Leanne, over to you.
Tēnā koutou, tēnā koutou. Tēnā koutou katoa. I'd like to begin by acknowledging SpaceBase co-founders Eric Dahlstrom and Emmeline Putt-Dahlstrom and thank them for organising this challenge. Can I also acknowledge Vicky Robertson of the Ministry for the Environment and representatives from the satellite company Planet, the United States Embassy and the New Zealand Space Agency. Can I also acknowledge and thank the panel of judges who've had a really challenging role. And last but by no means least, all of those who've entered the challenge as if the future of the planet depends on it, which it does, leveraging space technology to address carbon sequestration and coral health. Can I congratulate the grand prize winners in advance and look forward to your solutions being implemented in the region. Our city has had the pleasure of hosting the past two New Zealand Space and New Zealand Aerospace Challenges. And I have to say, I was enthralled when I heard the finalists making their presentations on both occasions. Not only do we have incredible capacity here in Aotearoa, it is also clear that our future is in very, very good hands. I have very high expectations of what we will hear this evening. No pressure. There is an incredible alignment between this challenge and our Council's strategic priorities, especially building climate resilience and building a sustainable future. Our vision is to position our city and region as the leading place to easily design, build and test cutting-edge technology, supporting students and innovators to create tomorrow's solutions to today's problems. I'm really looking forward to hearing what the Space for Planet Earth Challenge has achieved and where it will take us. Nō reira, tēnā koutou, tēnā koutou, tēnā rā tātou katoa.
Thank you so much, Leanne. It is now my pleasure to welcome Vicky Robertson. Vicky is the Chief Executive of the Ministry for the Environment. She's also the Secretary of the Ministry for the Environment. She's also the co-chair of the Aotearoa Circle, which is a coalition of public and private sector leaders committed to reversing the decline of New Zealand's natural capital. Vicky, over to you.
Tēnā koutou katoa. Congratulations. It's so inspiring to see all of you here participating in this event. Use of existing technology like satellites to create new insight in some of our most complex challenges. Data and evidence are really critical for the Ministry for the Environment, so it's fantastic to be able to support the event. So thank you for all getting involved. You know as much as I do, climate change is one of our most hardest challenges. It's going to take all of us over many years working as you are now, leading in your areas to try and tackle this complex change. We know that our emissions are the highest in 3 million years. We know that humans impact the warming of the planet. We see the weather events. We see sea level rising. We are at the cusp of thinking about the role of the oceans in climate change and how that can be combated. So the work that you're doing today through this challenge is so fantastic, and I thank you for leading in the areas that you can. And I really look forward to also seeing the results of your work today. Thank you for being involved. Keep going, and I'll look forward to the results. Have a great time. Tēnā koutou katoa.
And finally, it's my pleasure to introduce our next speaker. Now, honestly, as an MC, often when they ask you to introduce the sponsor, it's usually not the most fun part of the job. It's usually someone who's kind of trying to sell their products and making maybe a tenuous connection to the event. Not in this case. The lead partner and sponsor for the Space for Planet Earth Challenge is a company called Planet Labs. And representing Planet Labs here tonight is Dr. Tanya Harrison. Now, Dr. Harrison is a respected Mars expert who worked as a geoscientist and mission operations specialist on multiple NASA Mars missions over the past 13 years. She is a thought leader in the commercial space sector, and she currently works as the Director of Science Strategy for the federal arm of Planet Labs. Please welcome Dr. Harrison. Dr. Harrison, over to you.
Thank you so much, For those that aren't familiar with Planet, we operate a constellation of over 200 satellites that orbit the Earth every single day to image the entire landmass of the world to look for change, because we know that you can't manage what you can't measure. And with the impacts of climate change increasing in terms of rate and effects all around the world, you need to be able to monitor those changes as they're happening. And so when SpaceBase approached us to get involved with this challenge, we thought that this was a fantastic opportunity to see what creative minds at the high school and the undergraduate level and startups could do with this data set to figure out how we could use this to understand change in the world. We hope that data can be used to help build a sustainable world and really understand the human impact on it. We have more data coming down from space than ever before with satellites that are operated by companies and space agencies around the world. And now the key is to figure out how do we unlock the insights that are hidden in that data to really take action on them. And the presentations that I've seen so far from the teams earlier today were so amazing. I'm just blown away by the ideas and the ability that you've shown. And so I'm really looking forward to seeing your final presentations. And Planet is so proud to have been able to be a part of this competition. So congratulations to all the teams for making it this far. And we can't wait to see what you're going to work on next.
Thank you so much, Dr. Harrison. I have to say your bio is among the coolest bios I have ever had the privilege of reading. So wonderful to have you here and wonderful to have the support of Planet for this challenge. All right, on to the real stars of the show. It is time for the pitches. We're going to start with the high school category. Now, the high schoolers were given a problem statement relating to coral health. Coral reefs harbor Earth's highest biodiversity, host more than 1/4 of all marine fish species, and are also the global ecosystem under the greatest threat. Coral reefs are vitally important for global ocean ecology and biodiversity, as well as food production and economies of coastal communities, but they're under threat from pollution, from overfishing, and from the impacts of climate change, including ocean warming and acidification. But with the right information, local communities can act to help protect coral reefs. The challenge given to these high school teams is to help improve monitoring of coral reef health using satellite technology and help local communities protect coral reefs. All right, let's hear from our first team. Our first team is from Christ College. They are the Christ College team from Christchurch, New Zealand. Here representing the Christ College team is Tim Wang. Tim, over to you.
Unmute, Sabia. Okay. Good afternoon, everyone. We are the Christ College team, and we're very excited to present to you our innovative solution to monitor coral bleaching. Our team is comprised of 4 Year 13 students, and all of us share experience and a great interest in preserving our natural environment. I just want to come back to what this competition is all about, which is coral bleaching. So bleaching occurs due to rising sea temperatures, which puts corals under heat stress, and as a result, kills the coral's algae, meaning that the coral can no longer carry out its life processes. Now, because there is no algae, the coral becomes bleached, turning white, as you can see. And this is the most direct visual indicator that coral bleaching is occurring. Now, today, 25% of all marine life depend on healthy coral for food and shelter, but rising sea surface temperatures are threatening their existence.
The problem is current methods of data capture is simply ineffective. Firstly, today's data gathering requires researchers to fly over vast areas of coral, which requires an unsustainable amount of time, resources, and money. And also existing monitoring solutions provide information on bleaching that is solely based on data inference and not observations of the color of the coral, which is obviously the best indicator of coral bleaching. And also the average person who is interested in finding out more about coral will struggle to find useful information quickly.
Using the ESA Open Access Hub, we retrieve measurements of light from the Sentinel-2 remote sensing data. This is captured in 12 distinct light bands, each at different wavelengths like RGB and infrared. By collecting data in 12 different bands, we can capture changes that could be an indication of a bleaching event. The Allen Coral Atlas, shown on the right, is basically a tool that can help distinguish areas of coral from areas of land like rocks and vegetation around Aitutaki Island. By overlaying the Allen Coral Atlas data over the Sentinel-2, we can isolate pixels that we knew had the possibility of containing coral, as the purple markers show. After that, we simply chose 4 areas around Aitutaki Island and placed 10 data points, each surveying a 10 meter by 10 meter pixel in each area. This means that we can figure out the average reflectivity of each area in RGB and infrared bands. What we found was that by plotting the data gathered, the reflectivity of the coral increased in all light bands between August and December. This shows that the coral got brighter over that 6-month period. And the reflectivity of red and green light increased a lot more compared to blue. And since white is made up of red, green, and blue, the increased reflectivity tells us that this area became whiter. Now, this makes sense, right? Lighter colors like white have more reflectivity. And over the same time, the sea surface temperature increased as well. These temperature readings came from other satellite remote sensing missions. What's also interesting about these two graphs is that there's a correlating trend in both graphs. As the sea surface temperature increases, so does the reflectivity of RGB. By combining the RGB bands, we form blocks of color that you can see at the top of the screen, which shows a more direct and visual way that light reflecting off the coral is becoming brighter and whiter over time. So by harnessing satellite data, we found that it's pretty likely that there's a correlation between sea surface temperature and coral bleaching. I just want to show you how close our data's conclusions are to the real thing. So these are actually some images of the Great Barrier Reef, and you can actually see how similar our RGB formed images, our RGB formed color blocks are to these images of coral bleaching. But we still needed to find a way of confirming that our data's conclusions was actually accurate with what was happening.
So we developed a platform that combines our satellite remote sensing data with data from selected collaborators in the form of a website. The platform will be a way in which we can, 1, provide an easy-to-use interface where our partners at coral reefs can upload their data. This can include photos so that the public can get a more direct visual representation of what is actually happening. And 2, using our partners' data, we can then verify and calibrate our coral bleaching detection algorithm specifically for each region. And using AWS cloud computing, the website will periodically generate reports on the bleaching status of coral reefs with sufficient data. This can be really useful when coral bleaching can happen within 2 weeks, and it allows users to check up on coral near them. And having developed a prototype that could identify areas of coral and detect possible bleaching events, we needed local expertise to confirm our data's findings of bleaching by surveying the area in person. After we scraped through a database of international schools, we used the script to access the Allen Coral Atlas API, creating a roughly 50-kilometer by 50-kilometer box around all the schools. And after going through this process, we identified 13 schools from across the globe, which are near areas of coral, according to the Allen Coral Atlas API. So we emailed and invited all of them to collaborate with us on this project. And luckily for us, we received one very enthusiastic response from the Okinawa Amicus International School in Okinawa, Japan, who, like our school, is a Round Square organization member. The students and staff were also extremely passionate about coral and agreed to a long-term working relationship to confirm our findings. And as part of the collaboration, we were given access to underwater photos of local reefs, which are undergoing bleaching like the one shown on the slide. And also, we were given data like the one shown here, which displays the coverage of coral in the Okinawa area over a period of time. Going forward, our aim is to analyze the remote sensing data of Okinawa. And after identifying potential areas of coral that have been bleached, we will be able to test our system of informing locals of potentially bleached corals and asking them to look at the corals themselves. And once we do this, we will be able to apply our findings on a much bigger global scale. So what is our impact going to be? Well, with our system, we can now accurately find areas of bleaching and give a visual representation of the effect of bleaching, which will give us a much better understanding of the magnitude of bleaching around the world. And secondly, we can utilize our system to contact and notify locals of any unusual environmental changes, which is shown in our remote sensing data. Thirdly, because all of the data about bleaching is found on our centralized platform, anyone around the world with a computer can access our data. And also current solutions, they're all static, like the Allen Core Atlas and ReefWatch. And so what we can do with our prototype is we can add to them by providing coral color change. And so for the first time ever, we can directly monitor the effects of bleaching at an unprecedented level of accuracy. And so we hope that this will have a huge impact on monitoring and staying a step ahead of coral bleaching. Thank you for listening.
Wow. I don't know about you, that was an incredible way to start this evening's presentations. Particularly, I was particularly impressed by the collaboration with a school in Japan. You know, one of the things that we talk about a lot in the kind of disruption space is this awareness that the smartest people in the world don't work for you. I feel like those two gentlemen are among the smartest people that I've come across, and then for them to reach out to tap into some brains right across the planet, what a wonderful presentation. All right, on to the next one. The next one is from Cashmere High School, also here in Christchurch, New Zealand. It is the Cashmere Space Club, and representing the Cashmere Space Club is Charlie Trum. Over to you, Charlie.
Thank you for the introduction. Bear with me for a minute. We are the Cashmere High School Space Club, and I am Charlie. We have used satellite technology to monitor the effect shrimp farms have on coral reef ecosystems. Shrimp farms cause destruction of mangroves, which is commonly the nursery ground for the small fish that will later populate the coral reef ecosystem. A single shrimp farm will only produce shrimp for about 7 years and will continue polluting the environment for about a further 40. Next, I will talk about prototyping results. We used satellite data to find the location of shrimp farms. We looked at 2 possible areas, Java and Borneo, both in Indonesia, in which we found many suitable locations for case studies, which we used. And then we used Google Maps Street View to go down to the ground and to look to verify whether it actually is a shrimp farm. Then we used historical satellite imagery to find the age of the shrimp farm and whether the shrimp farm and whether it's abandoned or active. Finally, we used the Allen Core Atlas, a worldwide map of coral, to see whether it has coral near the shrimp farm. And then we see maybe there is rubble near the shrimp farm. Rubble is mostly broken coral. And then that tells us whether the shrimp farm has an effect on the coral. So this is case study 2. Here is a satellite image from Java, Indonesia. This shrimp farm was located manually using satellites and verified with Google Maps Street View for ground truthing. You can see the map of the Allen Core Atlas overlaid on the satellite image. Blue, which is coral, is away from the shrimp farm, whereas purple, which is rubble, which is dead pieces of coral, is around the areas where the shrimp farms are. This shows that the shrimp farm could be impacting the coral. Case study after case study, we keep on seeing the same pattern of shrimp farms next to rubble. An expert on coral reef biology also said to us that shrimp farms can have a detrimental effect on the coral reef ecosystems. Another way of verifying this is by looking through historical satellite imagery to see if the mangroves were cut down and whether the shrimp farm is abandoned or active. Now, I will talk about artificial intelligence. People could look through this data, every image manually. However, this is quite inefficient in a large-scale project. In the future, we're going to want a better, quicker method of doing this. This is where artificial intelligence and neural networks can come in. We have used neural networks to process imagery and come out with the result of whether this is or isn't a shrimp farm and do the process automatically. Next, I have experience in artificial intelligence and neural networks, especially the backpropagation algorithm coded in the Python programming language. Also, a low resource option is to use a set procedure manual without computers, but the artificial intelligence would be much quicker and easier. For the AI, we have already classified 7,000 images containing many case studies. All of this data was at least 70 gigabytes and growing. Here are the results of our neural network. I have trained this network to distinguish the difference between shrimp farms and forest using 4,000 images. This is a small portion of the 3,000 images used for testing. In this initial test, it got 100% correct. Next, I will show you a real-time video of my program running. So, I created a Python plugin. This is the Islander Java. This Python plugin is for QGIS mapping software. This is one of our case studies. I can do this neural network demonstration in real time. If I tell it to classify this neural network, it will tell me this is a shrimp farm. This is because every single one of these squares is a shrimp farm. It correctly identified this. Now, if I zoom into the forest over here, you can clearly see this is forest, but can the neural network see that this is forest? If I tell it to classify, it will say not shrimp farm because it cannot find any shrimp farm in this. That is correct, not shrimp farm. It correctly identified that that was not a shrimp farm. Thank you for watching. To make a difference, we plan on creating a traffic light classification system to classify the danger shrimp farms pose to coral reef ecosystems. This traffic light system can be used by governments, reef managers, NGOs, food supply chains, and others, and a general public awareness can be created using an education program. Packaging could be labeled with the traffic light level. Supply chains can market their product as environmentally friendly by using the green end of the traffic light spectrum. To sum up, coral reef ecosystems are affected by shrimp farming because the shrimp farms cut down the mangroves, and the mangroves provide a fish nursery for the fish that will later populate the coral reef ecosystem. Our project is feasible because you can see the shrimp farms with the satellites can be implemented and scaled. Our approach is novel because few, if any, people have tried this approach of combining research on coral reef ecosystems, shrimp farms, and mangroves using satellite technology. Also, shrimp farms are not usually considered a stressor to coral reef ecosystems, and especially not through mangrove destruction. We have used artificial intelligence and neural networks to automate finding of shrimp farms. We can also use a manual system without computers. However, the machine learning is much better. We can make a difference by using our traffic light system. To conclude, I would like to ask you, if you are a potential user of our project, please contact us through this challenge. Thank you.
Thank you so much, Charlie. What a fantastic presentation. To those of you watching at home or from your office or wherever you are, just so you know, this is the first time I'm seeing these presentations as well. And of course, I've got my video off, but I'm watching these presentations and my jaw is just dropping further. And I kind of feel like, can we just put these folks in charge now and just all the rest of us step back and leave it to them? I mean, such strong presentations right out the gate. Charlie, I will invite you to turn off your video. We'll hear back from you again later in the session. And then now it's my great pleasure to introduce our final high school team. This one is from Newlands College in Wellington, New Zealand. I love this team name. The team name is Not Basic. Here to represent Not Basic, please welcome Joshua Taefu. Joshua, over to you.
Talofa lava. It's my privilege today to represent Newlands College and the Not Basic team in presenting our project. Corals are one of the most important species alive, contributing to both marine ecosystems and coastal communities. Yet, coral reefs around the world are in immense danger. Over this presentation, our team looks to demonstrate a way in which we can better measure coral health and prevent future harm to coral reefs. But first, what problems are coral reefs actually facing? Well, the first is coral bleaching, the short-term coral killer. Coral bleaching is the process where corals lose their algae as they become stressed, leaving them with little ability to gain energy, ultimately leading to coral death. Bleaching, most strongly influenced by ocean temperatures, has become widespread in the modern age, with global warming resulting in more devastating and more frequent coral bleaching events. Decalcification, the long-term coral killer. While bleaching is critically important, another key risk to coral health is ocean acidification. As the ocean becomes more acidic, the skeleton of the corals dissolves, making the corals more vulnerable to both predators and ocean currents. While this issue isn't currently impacting corals strongly, in a few decades, it has the potential to pose as much a problem as coral bleaching. So the question is, how do we fix this? Our solution is using satellite technology and machine learning to predict coral bleaching. What makes this solution different? Well, first and foremost is its predictive abilities. While there's plenty of services displaying past and present coral health, there's an important lack of services predicting the future state of coral reefs. That's where we come in. By providing accurate coral forecasts, we're not only able to allow authorities and private organizations to act before it's too late, but to also use fewer resources in their response as the full extent of damage hasn't yet occurred. So let's have a look at the real thing. Prototype. What you can see now are sample sites taken from across the world, all continents, 48 of them to be exact, each representing a site with corals. And as any good group of scientists would, we turned it into a spreadsheet. Within that spreadsheet was all the satellite and coral bleaching data that we could find. From there, the data was analyzed through SageMaker, a cloud machine learning platform that established the crucial link between coral bleaching and the metrics we had retrieved. This was an intense training process where we selected the best models and methods that would produce the best results. The final outcome is an accurate and precise prediction model, allowing real-time data to be submitted with output being a prediction for each site. What you can see now is our most recent set of predictions, with green sites predicted to face minimal bleaching, yellow to face medium, and red sites at risk of experiencing severe bleaching events within the next month. Overall, you could say that this model allows us to predict future bleaching events by using those of the past. By passing through real-time current information, patterns and minute warning signs can be identified, allowing our model to predict where bleaching is most likely to next occur. And we think that's pretty cool. Impact. One obvious metric to measure the success of our project is its impact. We believe that the impact we can have not only today, but far into the future is huge. Why is this? Well, the first reason is the collaboration that's been ubiquitous throughout the entire development journey. As much as we wish we could, we can't take all the credit for the solution we've shown today. Throughout our project, we've received assistance in the form of insight, feedback, and validation from multiple stakeholders. This includes Professor Simon Davey, a marine biologist at Victoria University, Wellington, the Coral Gardeners Organization, the Ministry for the Environment, who are on this call tonight, and of course, the wonderful SpaceBase team. With Professor Davey, we came to understand how our solution would best help researchers if it was able to provide access to remote locations. Through Coral Gardeners and Ministry for the Environment, we saw how beneficial it would be for nonprofit organizations and government agencies if they knew about coral bleaching events in advance. And lastly, through the guidance of the SpaceBase team, we were able to see how that information and knowledge could be brought together to make the project you see today. This level of collaboration has led to a project which we believe could greatly benefit governments and organizations. To demonstrate this, we've made a three-step, three-year program highlighting the potential effects of our project. Year one, raising awareness. Of course, everyone has to start somewhere. Our impact journey would begin by starting conversations with authorities and organizations able to affect change, something that we've already begun to do. Through this, we'd hope to find more parties that would be benefited by our project. Year two, implementation. In our second year, our main focus would be initiating real change. Using our now established connections, we begin to help organizations like Coral Gardeners, as well as governmental departments and agencies like the Ministry for the Environment. In this context, we'll be both repairing the damage caused to corals in the past decade, but also improving coral reefs for the next. Specifically, for governments of lower socioeconomic status, knowing what corals are likely to be bleached incentivizes the replenishment of mangrove forests and introduction of fishing regulations. Two factors which reduce coral bleaching while improving coral health. Year three, expansion. From there, we'll look to expand our influence and further widen our impact. We'll do this by looking into other ways we can monitor and predict coral health, improving our ability to aid organizations. In this time, we also hope to see some fruits of our labor, seeing how corals have been selectively planted in certain locations which are less likely to be bleached. Next steps. While we think that all the stuff I've shown you tonight is pretty cool, we also realize that there's lots of work to be done and lots of untapped potential in our project. To this end, we've identified a few next steps that will increase our impact even further. Number one, finding or sourcing better bleaching data. By improving the quality and overall accuracy of our data inputs, our predictions will be made even more precise than they already are. Secondly, we would include decalcification as another metric in our learning model, allowing the second greatest danger to coral health to be predicted. Thirdly, we would look at circular economies around corals, using metrics such as atmospheric carbon dioxide as a proxy of coral bleaching. And finally, we would utilize autonomous vehicles like drones to further diversify our remote sensing, enabling us to better understand the health of corals deeper in the ocean. Conclusion. Corals are one of the most important species alive. Yet, in the future, this could very well change without human intervention. In our eyes, we see this project as a step forward to achieving this goal and aiding coral reefs. Thank you for your support.
Wonderful presentation, Joshua. Thank you so much for that. One thing I really loved about that was the identification of the potential of coral reef circular economies. The philosopher Osho said that you can't sit in a dark room and say, go away dark. You can't chase dark with dark. But all you have to do is light a single match and the dark will go away. And sometimes when we're thinking about the damage we're doing to the planet, can be tempting for us to focus on all the things we're doing wrong and say, we need all this stuff to go away. But if we can think about where we're heading, what the opportunities are, I think the possibilities are unlimited. Right. That's the high school group. I am so glad I'm not a judge for this. It is time for us to move on to the university startup category. And the university startup teams were given a challenge relating to carbon sequestration. Now, to combat climate change, we have to reduce global greenhouse gases such as carbon dioxide. And one way that we can do that is by increasing the absorption and containment of carbon dioxide through sequestration in biomass, like forest areas. But if we can employ satellite technology to monitor and detect carbon sequestration in other zones, like native bush, like pastures, wetlands, coastal zones, then we can create incentives for landowners to sequester more carbon through changes in land management. And so that'll allow us to develop tools that can monitor carbon sequestration to address climate change on a global scale. The problem statement that was issued to these teams is to use satellite data in combination with other data sources to help develop verifiable methods of measuring carbon sequestration on land or in coastal areas. The first team we're going to hear from is from Brisbane, Australia. They are PhD students from the University of Queensland. They're called the Lidar team, and speaking on their behalf is Ana Ruiz Beltran. Ana Ruiz Beltran, over to you.
Thank you very much, Kaila, for your introduction. First of all, we would like to acknowledge the traditional owners of the lands and waters from which I am talking today, and as the Lidar team, we offer our respect to elders past, present, and future. Hello, everyone. My name is Ana Patricia Ruiz, and with Tim and Jason, we are forming the Lidar team. So we are participating in this challenge to solve a problem. So what's the problem? There's an increasing need for a carbon accounting. So industry, forest degradation, bushfires, all these processes emit carbon, CO2 to the atmosphere, but at the same time, as it was mentioned before, this carbon can be reabsorbed by the forest. If we want to understand climate change, carbon accounting needs to be reliable and needs to have accurate data. So this is also going to increase the credibility of the carbon offsets. So yeah, we need to provide a verifiable method that will help us to know how accurate our carbon storage estimations are. So, and this is where our projects comes in, because we will fit that gap by delivering a service that will help to increase the accuracy of the carbon accounting to make smart evidence decisions towards a sustainable future. So the weight of the trees, the biomass, it's composed around 50% of the carbon. So we need to weigh the trees to create these estimations. So if we want to make this on a large scale on a map, we need two key components. The first one is data gathered by sensors in space, and the second one is data collected from the ground. So the sensors in space, they need to be sensitive to the forest structure because the branches, the trunk, the canopy, the sum of all these components form the above ground biomass. So let's talk about JEDI. JEDI is a sensor that it is on the International Space Station, and it's developed, well, was developed to quantify carbon forest structure. So JEDI functions like a flash from a camera, and all the components that from the tree structure are censored and they are delivered in a waveform. So this Lidar waveform provides key vegetational structural information for inferring biomass. For example, if you look at the image here, you will see how we can see a prototype JEDI of canopy height. Right now, more than 10 video shots have been collected in the first 2 years of the functioning of this sensor, but it's only about 4% of the land. If we can see really clearly the Amazon forest. We can see really clearly the desert areas of Australia that they have low canopy height, and these other areas like the Amazon really high canopy height. So if we look at this area of Australia with JEDI, we can see that there's a lot of gaps there. So each one of these points represent a JEDI footprint of 25 meters diameters, but it's not everywhere, so we need to fill the gaps. So to fill the gaps, we're gonna use Planet Toe, imagery, and Sentinel-2. So, well, this is really nice, but how can we translate this into biomass and use for mapping? Then the satellite needs to be matched to the second component that I mentioned before, which is data collected from the ground. So in the past, and now currently, we use tree metrics such as diameter and breast height. You can see the little researcher taking one of these measurements. And with these measurements, we infer with some empirical equations what's the biomass of the trees. But research is showing that this method is inaccurate. So this can be a significant source of bias when it's scaling carbon sequestration over large areas. And if you are talking about the carbon, about the government, a national government giving these estimates, it's not a good idea. So what we're doing? Well, a method that has increasing its popularity during the last years is the terrestrial laser scanners. So the terrestrial laser scanner uses lasers, or uses LiDAR as well, and these acquire really, really accurate data at a millimetrical precision. So we have really dense point clouds of all the components of the trees, and with these estimations, we can estimate metrics. We can estimate the volume of the tree in a very automated fashion using computers. For instance, we had these vegetation point clouds and processed them using a deep learning algorithm that segments even the trees from the trunk, and then we only have the wood biomass. And with this, we estimated the above ground biomass on the ground. So then, yes, this idea sounds very appealing, but does it work? Well, yes, we produce a model using a machine learning algorithm, which is called random forest, because it has shown that it's so far the best algorithm to do this kind of regressor. And it's not called random forest because it's pop forest, but it's just the name. So we tested it in a woody savanna in the north of Australia, the site I showed you before. And we know very clearly the pathways that we need to address to improve this model, also to scale it up to several sites in a continental level. So all our code is in open source, and our analysis can be run in cloud computing platforms like AWS or Azure. And if you were curious to check this QR code, it's not to check that you're double vaccinated. You can you will be seeing our GitHub repository, which is still in early development, but you can actually now get the codes and run it for yourself for the satellite imagery. There are several companies that use different methods to measure carbon storage and also to provide forestry products. And we could potentially make a partnership with them so we can leverage our capacity and improve the method. We would like to thank all the people who assist us towards access to the research sites, the funding, the concept advice we're getting from them. And thank you so much, Sean, Levig, and Stuart Fink for your valuable advice. Well, in summary, our project integrates novel field and satellite measurements to develop a verifiable method that will help us to know how accurate are our carbon storage in a scalable, time, and resource-efficient way. We're going to provide a service that delivers data that is essential for science, industry, and governments for the sustainable use of ecosystems. Thank you very much, and stay safe.
Thank you so much, Ana Patricia. What a fantastic presentation. So exciting, the potential of using LiDAR and satellite data in order to give us power. And that's what information is, isn't it? It's power. It gives us the power to be able to understand what's happening so that we can decide how we want to take steps in order to positively impact our direction of travel. Right. Our second university startup team is from Auckland, New Zealand. It is comprised of graduate students from the University of Auckland. They are called the HEAL Initiative, H-E-A-L. That's in all caps. I'm wondering if it's an acronym. Representing the HEAL Initiative is Mikhail Sayat. Mikhail, welcome, and over to you.
Awesome. Thank you very much. So good afternoon, everyone. My name is Mikhail Sayat, and today I am very excited to talk to you about the HEAL Initiative. We consist of 4 members ranging from undergraduate to PhD students at the University of Auckland and have backgrounds in engineering, physics, and biology. We all met when we started a space club at the university, and our shared passions for space, sustainability, and especially the growth of the New Zealand space industry have brought about the company, the HEAL Initiative, a data agency to tackle climate change. So we have identified 6 needs to address the tracking of carbon sequestration to tackle climate change: the need for trusted and accurate carbon sequestration measurements, the need for data to be frequently updated, the need for a cheap but effective solution, the need to identify where carbon is stored, the need for a very scalable solution, and a need to be able to survey large locations to find where the carbon is. Enter the HEAL Initiative, an agent to provide trusted and accurate measurements of carbon sequestration over a specified area and time by using frequent satellite imagery to survey large areas on Earth. The trusted and accurate information will then help governments to create appropriate policies, academics for research and development, industry to drive climate change mitigation, and most importantly, climate change mitigation efforts to deploy effective strategies. This will allow locations such as forests, where lots of carbon is stored, to be conserved. And in addition, climate change mitigation efforts can be directed to locations where low levels of carbon is, such as cities. This leads to an overall healthier and cleaner environment. So how do we go about doing this? First, we get a request from users such as yourselves on where and when you would like to know about carbon storage contents. We then download satellite images of the exact area and time from a satellite imaging company such as Planet Labs, who are here with us today. With the help of QGIS, a software tool, we scan these images, extract the red, green, blue, and near-infrared data of certain objects of interest so that we can train our machine learning algorithm to identify these objects in the future. Using a decision tree and the trained algorithm, we are then able to identify what each pixel is on the satellite image. With these classified pixels, we identify which ones store carbon, and based on the total area they accommodate, using carbon models to calculate the carbon stored in the overall satellite image, providing you with a spatiotemporal carbon sequestration measurement. To fully show you this process in effect, here are pictures of satellite imagery of West Auckland from 2017 to 2021. And in this case, we chose 3 carbon storing objects: trees, mangroves, and grass to be identified. Again, this can be extended to anything we want to put into our algorithm. As we can see, the trees are correctly identified in the west, in the Waitakere Ranges, and mangroves such on the right in the Northwestern Motorway and Rosebank. With these pixels, these objects accommodate, we can calculate the area they take up. Using models of how much these objects store from literature and the New Zealand Emissions Trading Scheme, we calculated the total carbon stored based off these objects in this area over time. Currently, this minimum viable product has been developed offline. However, we are currently developing it to be online on a website for free for anyone and everyone to use. We are also in the ideation stage of an app to personalize the tracking of carbon so everyone can contribute. With an injection of Kickstart capital, our business model is self-sustaining. All of our expenses will go into research and development, where we can produce trusted and accurate data. We then provide services to provide this data for free, like the website, but with fees and services that are more individualized and specialized for the client. In developing our solution to this challenge, we realized that the solution of using machine learning is very cost-effective and scalable. So we proposed the Humans for Earth and Life working group, where we could collaborate with local councils on certain problems, have a presence in different universities to collaborate with students and researchers, and have commercial services such as the HEAL initiative to drive innovation, a developing vision for a national collaborative society to tackle local and global issues. In our conversations with experts and specialists on the topic of measuring carbon, we encountered recurring problems. Data on carbon content took too much time, effort, and resources to collect. Clients had to go to certain institutes to have their carbon contents audited for a fee, and this would take a very long time. With our solution of using frequent satellite imagery that will be free for anyone on a website, all of these problems would be mitigated. And the solution we present is cost-effective, and we see this as an opportunity to be very scalable and go global, where we could collaborate with local researchers to produce accurate data so users can access needed information in tackling climate change. On top of this, our same solution has attracted work with the Large Binocular Telescope Observatory in Arizona, USA, where we will employ our machine learning algorithms to solve astronomical issues. And we are currently waiting on the confirmation to collaborate with them. Our immediate next step comes twofold. Launch the website for anyone to use and grow the team, especially for research and development. Other works include developing our models and solutions, collaborating with more stakeholders, and reaching out to the public with what we are doing. To conclude, we would like to thank our collaborators for helping us develop the HEAL initiative. Furthermore, with our shared networks, such as NASA JPL, the University of Auckland, and SpaceBase, we are more than ever ready to work with our stakeholders, help mitigate climate change, but also expand our capabilities. Thank you all for listening. And if you would like to know more about us, our upcoming projects, or would like to collaborate with us, please do not hesitate to contact us and visit our website, healinitiative.space. Thank you very much for listening.
What a fantastic presentation, Mikhail. Thank you so much for that. I love it. I have to say, prior to this evening, I didn't even know that spatiotemporal carbon sequestration measurements were a thing, and now I want them now. I also am really glad that my question around the acronym got resolved, Humans for Earth and Life. And I love the thoughtfulness that went into identifying what are the specific problems that this project was aiming to address, what were the needs that this solution could potentially mitigate. So well done to you, and we are now up to our final presentation for the university startup category. This presentation comes from Suva, Fiji. It is the Yadrava Vanua Environment Watch team. This team includes students and researchers from the Universities of the South Pacific, which is USP, as well as 6 other academic institutions across Fiji, Australia, and New Zealand. Those are the Fiji National University, the University of Fiji, University of Western Australia, University of Canterbury, and the Australian National University. Representing Yadrava Vanua, please welcome Nicholas Metherall. Nicholas, over to you.
Kia ora, and thank you, Kaila, for that introduction. I'm just going to share my screen with sound. More than 420 million hectares of forests have been lost since 1990. This has had deep impacts on connected ecosystems and livelihood. In Fiji, during the 2012 floods, Wavu Wavu village was destroyed. This was the first village in Fiji to be relocated. due to climate change. This also occurred because of the clearing of vegetation and riverbank erosion, leading to streambank collapse, forcing villages to move. So how can we protect vegetation and reduce the risks of this? So there's possible with carbon projects to help us do this. However, there are two main difficulties: long-term spatial and temporal MRV, as well as supporting communities to access fair deal for the benefits and consultation. So how is Yadrava and Vanua addressing this? So there are 4 things that we've done in order to address this issue. Firstly, we've analysed remote sensing and GIS data for project area selection, and we've looked at the historic trends, the current stocks, and the future modelling of CO2. Then we've accessed open satellite imagery, and we've done a land cover stratification in Google Earth Engine, and we've brought in the emissions values and joined them with open source QGIS.
Third, we're not seeing your charts.
Oh, wait, one sec. I'm just sharing again. 1 second. Excuse me. Yep. So yeah, the third thing we're doing, you can see now?
Yes.
Yeah, the third thing we're doing is leveraging planet satellite imagery with machine learning to count individual trees. And all of this is being done through co-design with local researchers, government, and communities in order to ensure that we meet the local needs and can be verified. So the first stage is site selection and baselining. So we use Sentinel imagery, first of all, and then we incorporate historic deforestation imagery. We do a land cover classification, and we use elevation to work out the areas where there's flood risk, and also soil to work out the areas of landslide risk. We selected this case study based on these to optimize our environmental impact. Next, we did our land cover classification, and this was done using 10-meter Sentinel imagery. We incorporated elevation, biomass, infrared, and vegetation indices. And this is our land cover result. We achieved a 97% accuracy level through our validation process. And then we next extracted different layers of land cover, including agriculture, grasslands, mangroves, and forests. And this is the results for our areas in hectares. So this is what we've generated. However, we also had to work out the different types of biomass for different zones, upland and lowland, and different types of forest. And through this, we're able to then work out this total CO2 stock. So what you're seeing is the current stocks for Fiji at this point in time. But then we can also do modeling to also capture soil carbon using the Rothsea soil carbon model. And this is also a requirement for verification. The next stage was to use the planet satellite imagery through SpaceBase. And this helps us to improve our estimates. So this process involved using Jupyter notebooks. We did training using different bands of satellite imagery. And this is an example area that you can see here. This includes some of the gray areas, the patchy areas captured as parts of forest. However, you can actually see that there's a lot of trees and plants outside of these forests that are not yet being captured. And so our approach helps to capture these. So what we're doing is we incorporate the satellite imagery and the planet imagery, and we can do training through field measurement. So our team went out to the field. These are pictures of us measuring these trees at this site in Fiji. And so we measured these trees and used it to train our machine learning to do identification, segmentation, and counting of trees and replicate this process more widely. The business case for this would be that once we've identified the tree, as we did here, a rain tree, we can then work out the biomass over time and convert this to CO2 over time. And each ton of CO2 is equivalent to carbon credit. So over 30 years from this one tree, we would get about 0.94 tons for this rain tree. And over a 30-year carbon credit project, you would get about, for that 1 hectare of 15 trees, maybe $700 to $1,400 US. But this is just that 1 hectare plot. So with our remote sensing and our machine learning, we're able to replicate this process more widely and capture 200,000 across the floodplain and 4 million tons of CO2 sequestration. So we've actually, these are our outputs and our results that we've already calculated through our prototype. None of this would be possible without our community-based fieldwork and working with our team. This is our team measuring trees. We've done a lot of mangrove forestry inventories as well. And also this is our fieldwork validation and verification at the site that you saw earlier. And this is all part of our implementation plan for verification. So we've done a detailed Gantt chart to plan all this out to fit within verification frameworks, including government frameworks and the voluntary market. And this allows for adoption and scaling up over time. And this allows us to apply it in Fiji and internationally through our capacity building. Our collaboration involves the Ministry of Forestry. We've also learned from the University of Copenhagen, Global Evergreening Alliance and Planet for machine learning. But most importantly, working with local communities is the key here, because we want to ensure that we can create work opportunities for MRV into the future. And this will help training the machine learning, but none of the remote sensing will be of any value without this field data collection as well. So it's really important that we continue to work with communities and support their livelihoods for stewardship. And this is represented in our team. We have a really interdisciplinary team from multiple institutions. And you can see here that we have a mangrove team, a forest team, and a GIS and remote sensing team from across Fiji, Australia, and New Zealand. If selected, our future plans are to, 1, use the sub-meter SkySat imagery tasking from Planet to expand and improve our machine learning and training across the region and more widely. Secondly, to do capacity building to share our methods and outputs for ongoing MRV, fieldwork and ground truthing. And lastly, we want to continue to do our community-based mangrove and tree planting initiatives, including in Wavu Wavu village that you saw at the beginning and other disaster recovery areas. Thank you for your consideration. Tinaka level.
Thank you so much for that wonderful presentation. That was our final presentation from the university finalists. From Yadrava na Vanua. Thank you so much, Nicholas. That was just fantastic. Yet another incredible example of using this satellite imagery in order to provide a positive impact for our planet. I will invite you to turn off your video now. Thank you. And I will just say, right at the beginning of this evening's festivities, I thanked the judges. I had no idea when I thanked them exactly what I was thanking them for. And now really I can see just how challenging the role ahead is for them. Right, we are running a little bit early this evening, and what we're going to do, because that job is so challenging for the judges, we're going to make sure they have enough time. So we're going to, instead of taking a 15-minute break, we're going to take a 20-minute break. It is currently 6:05. We're going to take a break. We've got some slides that'll show you a bunch of information, including what the prizes are, etc. And we will come back to you at 6:25 to learn who our winners are. See you in 20 minutes. No mai hoki mai kia koutou. Welcome back, everyone. Wonderful to have you with us to hear who won the prizes, who are our winners. We are going to start with the high school category. One of our major sponsors of the challenge competition is the New Zealand Space Agency and MBIE. Here to present the high school grand prize is Dimitri Geidelberg. Dimitri is the principal advisor to the agency, and he is focused on strategic relationships and international science partnership for the agency. Dimitri, welcome, and over to you.
Tēnā koutou katoa, nisambula vinaka. Good evening, everyone. Thank you very much, Kaila, for that introduction. I'm really grateful for SpaceBase and the organisers for inviting me here this afternoon for the award presentation. The name of this challenge, Space for Planet Earth, says a lot. So much space activity is undertaken to provide us with the data and signals that allow us to understand our planet and the impacts that our activities are having, as well as giving us the information and tools to use our resources more efficiently and to reduce that impact. It's for this reason that New Zealand's, by way of example, New Zealand's first official space mission collaboration, we've partnered with the Environmental Defence Fund in MethaneSat. MethaneSat is a remote sensing mission focused on methane. The information that will derive from MethaneSat will be used to take action to reduce methane emissions, primarily from the oil and gas sector, and will slow down, hopefully, if we're successful, slow down the rate of climate change. To have the capable workers of tomorrow means investing in the students of today. And data challenges provide students with the opportunity to test and grow their skills while working with valuable data sets. It provides them that opportunity to come up with solutions to real world problems. And a number of years ago, in the early days of the space agency, we partnered in a number of challenges and hackathons with partners such as Airbus, with Xera, with SpaceBase, and a range of others. Last April, I was very pleased to kick off Taki Waihere, the New Zealand Geospatial Hackathon, which we ran in conjunction with Maxar Technologies. Under the first activity ran under our partnership, under the Innovative Partnerships Program with Maxar. And so this year, of course, we're delighted to be a sponsor for Space for Planet Earth. I want to acknowledge the very hard work and the generous contributions, rather, of SpaceBase, Planet, all the organisers, the mentors, the judges who've worked very hard over the last few months to make this event the success that it is. And of course, I really want to commend the high school teams, notably the three finalists here today. I just want to say that I've been extremely impressed with the sophistication of the solutions that have been developed, by the approach of looking for different data sources to incorporate into those solutions, to reaching out to other organizations, establishing partnerships to make these more effective, and of course, the quality of the presentations that we've heard here today. Before I announce the winner, you may have seen it on screen during the break, but before I announce the winner, I just want to recap the prizes rather, that the winners will receive. And this is an amazing prize, $10,000 in cash, a Planet data voucher to the tune of $15,000, and a scholarship to the Mars Virtual Academy Analog Astronautics program. So this is really an epic prize, and definitely worth doing your best for in this competition. So it is my great pleasure to announce the winners, and they are Not Basic from Newlands College.
Hello, thank you so much. Oh, you can't actually see us properly, but we're here.
Okay. Green screen's acting up a little bit. That's okay. We're all here. Yes.
It's been really nice to compete in this competition, especially with the support from everyone, and we're really thankful to reach this stage. We'd like to thank everyone for their time, especially the judges here today. And we're really happy. We just shouted very loudly before our meeting.
Start the neighbors.
Thank you so much.
Thank you.
Thank you very much.
Yeah, well, I think you deserve to shout loudly. You did extremely well. You've really done yourselves and your school proud, and you've won a set of awesome prizes. So congratulations.
Thank you so much.
Wow, so exciting. Huge congratulations to Joshua and the whole Not Basic team. It was fantastic to get to see all of you in there and to hear the excitement coming through from you. You did an absolutely phenomenal job, and so did all of our high school teams and finalists. What a wonderful outcome from this evening's presentations. Thank you so much, Dimitri. Thank you so much, New Zealand Space Agency. Congratulations once again to the Not Basic team. All right, now we are going to move on to the winners of the university startup category. And to present this category, we're going to welcome someone from the U.S. Embassy. The U.S. Embassy, you can probably hear from my voice that I'm not originally from Aotearoa, New Zealand. I've been here 17 years, and this is absolutely Kainga for me. This is home now. I became a citizen 10 years ago. You're not getting rid of me, but I was born and bred in the United States of America, and so I do have a special place in my heart for the U.S. Embassy. The embassy has been a huge supporter of New Zealand's space initiatives and programs, and they are a gold sponsor of the challenge. So here to announce the winner of the university startup category is Angela Kennedy, who is the public affairs officer for the embassy in New Zealand. Let me just make sure Angela is here to join us.
Hi, I'm here.
Hi, Angela. Great to see you. Over to you.
Thanks so much. Sorry, I had to join in as someone else's name. Before I announce the other prize, I did want to just quickly mention one of the conversations the judges had just now was we would like to have an additional honorable mention prize awarded later based on a really eloquent and engaging speech to Charlie from Cashmere Space Club. So Charlie, we don't know what the award will be quite yet, what the prize will be, but we wanted to just make sure that you knew we all really appreciated the presentation you gave.
Thank you so much. This is so much fun.
You are welcome. You deserved it. Your whole team did a great job. And like Kaila said, we're impressed with all of the teams, and we wish we could give everyone all of the prizes.
Thank you so much. This is great.
You're welcome, Charlie. Well, I'll get back to the next prize at hand, and just to say it really is my honor to be here with you all today representing the U.S. mission to New Zealand and Samoa, and to be here in support of SpaceBase and their Space for Planet Earth Challenge. This is a project and something that we're particularly excited to support because of the strong and the clear connection between the US and New Zealand in both space and climate change issues. Just look at some of the upcoming things that we've had going on, or COP26, the climate change conference that just happened recently. We've got that Artemis launch coming up, and New Zealand signed on to the Artemis Accords recently that established space exploration cooperation principles. What a mouthful, for the 21st century. So we can look at the effects that climate change is having in our region when we look at carbon sequestration and coral health, for example, as shown by today's challenges. So this is obviously a key priority area for both of our countries, and another area that we're just all very aware international cooperation is crucial to successful mitigation in the future. And that's why the US invests in and supports new and innovative solutions to these ideas. And that's why we are so happy to invest and support this specific program today. And quite frankly, Kaila had it spot on when she said we had a tough job as judges deciding what to do with all of these amazing programs that you guys have come up with, all 6 teams today. I just want to make sure you are aware that all of you are change makers. You're all doing amazing things. And I'm just humbled to be in the same virtual space as you all today. So I want to thank you all, congratulate you all on a job well done. And scoring really was very difficult and very tight. So let me also remind you what the University Startup Level Grand Prize is. That would be 30,000 New Zealand dollars cash, a Planet Data voucher worth an additional 15,000 New Zealand dollars, and 6 months of SpaceBase mentorship, which we all know is obviously priceless. So that is with my distinct honor and privilege to, without further ado, announce the University Startup Grand Prize winner. And that team is Yadrava na Vanua. Congratulations.
Thank you so much. Thank you very much. I'm just wondering if any of my team, if the team is here. Anyone else? I think because we were all in the other presentation we did earlier today, but I think they're all watching on, I think they're all watching, so they can't see this, but I just want to say Vinaka Vakalevu to the whole team, Salote, Lency, Arti, Tale, Dema, Pauline, Nathan, Hilda, Beth, Francis, Juan, and yeah, just everyone, I'm sorry if I've forgotten anyone, and thank you to the SpaceBase, Emmeline and Eric. You guys have lost, I think, a lot of sleep organizing all of this. It's a huge commitment, and look, we really appreciate it. We worked really hard, and I'm hoping that we can create a lot of opportunities for the researchers in the Pacific, and a lot of funding for them to do more work on this project. So thank you very much, Angela, and thank you. Yeah, thank you, everyone.
Congratulations again. You guys did an amazing job. Oh, and more team members, please. I think that might be Nicholas. You are muted. So if you are, there you go.
Yeah. No, thank you. I'm just, I think our team is all here. They're all on like Facebook messaging, but I think they're watching. I don't think they can speak because we only got one speaker's link. So, but everyone is really appreciative, and thank you. We really weren't expecting that at all. So thank you so much.
Congratulations. Kaila, I'll pass it back to you.
Thank you so much, Angela, and huge congratulations to you, Nicholas, and the entire Yadrava na Vanua team. What a wonderful outcome. Huge congratulations to all of the university startup teams. Again, you know, such a challenging role for those judges. To all of the finalists who were here presenting tonight, oh my gosh, just a really fantastic job. They're, you know, somebody kind of has to win these things, but it's been absolutely incredible to listen to every one of these pitches. Right. It is now my honor to introduce really the folks who are behind this event, behind not only this event this evening, but behind the entire challenge. The Space for Planet Earth Challenge is the brainchild of SpaceBase. SpaceBase is a social enterprise focused on catalyzing space entrepreneurial ecosystems in emerging and developing countries. They're doing this from Aotearoa, New Zealand. It was founded by Edmund Hillary Fellows, Emmeline, Pat Dahlstrom, and Eric Dahlstrom, who are originally from the US. They've spent 5 years working on growing the space industry here in New Zealand. They're having a huge impact on women in New Zealand's growing space industry and ecosystem. I've known them for a long time. It's an honor to call them friends. Emmeline and Eric, over to you.
Thank you so much, Kaila. Yeah, again, thank you, everybody. And first of all, huge congratulations to both the grand prize winners. Fantastic presentations. I mean, I think our jaws were dropping, and just to see kind of the journey that we've gone through all together, basically when we start the incubator, is just an amazing thing to see. So Not Basic and Yadrava na Vanua, yeah, great job today.
And yeah, we've been amazed at how prize challenges can really bring out all this innovation that is in the region. And we really hope that all these projects can continue and build collaboration and cooperation together.
So before we end, I just basically wanted to make sure that we thank everybody that has been involved with the project and the program, of which, you know, without all of you, we would not be here. So first, our main partner, Planet, who has been providing the data and also the sponsorship to leverage the satellite data to address the problems that we're like focusing on. Thank you so much for all your support. We want to thank all of our sponsors, for which without them, again, this program would not be possible. To the US Embassy, K1W1, ChristchurchNZ, the New Zealand Space Agency and MB, Consegna.cloud, Clare Foundation, Greenlight Ventures, Namaste Foundation, Engineering Dreams, Christchurch City Council, and the MMAARS Academy for your generous support. We also want to thank all of the speakers, the mentors, and the advisors who helped us during the 2.5 months online research incubator that we went through with all of the 12 teams. We also wanted to thank all of the judges for basically helping also evaluate, starting from down selecting to the 12 teams in the incubator, to down selecting to the finalists, and of course the judges today that helped us, which was very, very hard, as we were seeing kind of like as a fly on the wall. We want to thank also all of the organizations that help promote and also recruit for the teams during this time period. And of course, we want to thank the applicants and the teams who went through this with us. We are really hoping to see what comes out of this. This is only the beginning, and we look forward to all of the collaborations and everything that we could potentially still work on together. So lastly, we thank you, the audience, for actually being here with us as well, and listening to the presentations and celebrating the impact with us. So ngā mihi, and back to you, Kaila.
Thank you so much, Emmeline and Eric. These things do not happen without someone taking their own initiative to have a dream and then taking massive action to turn that dream into reality. You are the ones who turned a dream of hosting this competition into a reality. We are so grateful to you for having done it. And certainly from what we've seen tonight, the fact that you took the initiative to do this is going to yield incredible positive impact for our planet for years to come. Right, that is us for the evening, folks. It's been such a joy to be a part of this with you, such a joy to hear these presentations from our high school teams, from our university and startup teams. I feel very optimistic about the future, knowing that we've got folks like this working on some of the really super challenging problems that we're facing. Huge congratulations again to our grand prize winners. Huge congratulations again to every one of the teams for becoming finalists, for all of the work that you've put in. You are the change makers. You are the ones who are going to make these things happen. Thank you so much, everybody. Kia kaha, kia maru, kia atawhai. Be strong, be calm, be kind. Have a great night. Take good care.